So this video will be an example of estimating the error in a calculated value using a differential. And there are two standard ways to get started notation to use. So what I do might differ somewhat from what you might see in a textbook or some other video or website. So this problem says that a ball bearing is measured to have a diameter of 8 millimeters. If the measuring device is accurate to 100 micrometers, because nothing's perfect, use a differential to estimate the absolute and relative error when using d equals 8 to calculate the volume. So I'm going to need to use the formula for the volume of a sphere, right? The ball bearing. So I'm going to need to use v equals 4/3 pi r cubed, right? That's the volume of a sphere based on the radius. Now I'm given a diameter value, so I'm going to need to convert that into a radius value. So if the diameter is 8, then the radius would be 4, right? So r equals 4. So I could plug in 4 and get, the volume equals whatever, which we'll do in a few minutes. But I could calculate that, right? Well, I want to know what's the error because the measuring device is not perfect. It's going to be off by a little bit, up to 100 micrometers. So I want to convert that into a usable number. So if the diameter is accurate up to 100 micrometers, then the radius, while being half the diameter, would be accurate to 50 micrometers. So I'll say that dr, the differential of the radius, so the small change in the radius, you could think of as being like the error in the radius. This is going to be 50 micrometers, right? Now, we have our radius, I didn't write it, I probably should, is in millimeters. It's written up here for the diameter, but I forgot to write it for the 4. So, up just a little bit. Okay, so I really want either everything in millimeters or everything in micrometers, but having the volume in micrometers might be a bit of a pain. It might be a really large number, so I'll go with millimeters. So I need to convert this 50 micrometers to millimeters. And basically, from millimeters to micrometers is a ratio of 1,000 to 1, or 1 to 1,000, I mean. So 1 millimeter is 1,000 micrometers. So this is going to equal 0.05 millimeters. So 1/2 of 1/10 of a millimeter. Okay. So that means that the radius is really between 3.95 millimeters and 4.05 millimeters, which is hinting at a different way to write this, but I'll avoid that at least for now. Maybe at the end I'll point out here's another way to write this, but I'll stick to this approach for now. So the first thing I can say is, well, that means the volume, because I am going to want the volume when I go to find the relative error. The volume will be 4/3. Again, the calculated volume, not necessarily the actual volume. 4/3 pi times 4 cubed. So that's 4 cubed is 64. Times 4 is 256. So that'd be 256 pi over 3. Of course, this is cubic millimeters. Okay, that's just the volume formula. So, and if we wanted a decimal, we could do that. We don't need that right now. But if we did, we would maybe want a decimal. It's going to be like 270, something like that, millimeters cubed. But we really, well, that's fine, but we want to, well, yeah, but how accurate is that? When you have an error involved in the radius measurement, how does that translate into the volume measurement? Is that off by a lot or by a little bit? So what I'm going to do is I'm going to find the differential of v as a function of r and dr. Okay, so when describing how to do this, one thing is to say, well, we previously said that whenever you have some function, I'm going to erase this part, but I just want to review something we talked about before in a previous video. I can change my color here. Okay, sometimes the that app freezes. Inconveniently, sometimes when I'm making a video. Anyway, so if you have y equals f of x, y is some function of x, then dy, the differential of the output variable, is equal to the derivative of the function times dx, the differential of the input variable. And if you think about taking this equation and dividing by dx on both sides, you'll get dy over dx equals f prime of x. you might say, hey, that's just saying that the derivative in the Leibniz notation is equal to the derivative in the Lagrange notation. Sort of. This behavior, this is, I think I'm not a historian, but I think this is one of the reasons why Leibniz liked that notation, the dy dx notation, which previously we never called dy over dx. We called it dy dx because it wasn't a fraction, it was just notation. However, when you are talking about differentials and you divide dx on both sides, you have a genuine fraction. So this alone is not a justification for saying what a differential is. It's just a reminder of this is the conclusion we reached when we talked about what a differential is. Again, the differential in the x-coordinate is a tiny change in the x-coordinate. And then the differential in the y-coordinate is like, well, when you track the tangent line and you move horizontally by dx, where do you move in the y-coordinate? Well, that's dy. Okay, so that's just a quick reminder of this. So what I'm going to do is I'm going to do this with the volume function. Okay, volume is a function of r. So I'm going to have dv equals the derivative of this function times dr. Okay. There are other ways to think about this, but they're more of they're analogies that maybe help you get the right result, but aren't technically correct. And I'm going to avoid talking about those in a video like this. So dv, the differential in the output variable, well, that's going to be the derivative of the function times the differential of the input variable. Well, the derivative of this, I'm going to use the power rule of 4/3 pi times 3r squared, which I could cut corners, but I won't do just yet. You might see what I mean when I write it. Times the differential of the input variable, dr. You might notice that really I probably could have just said 4/3 times 3 is going to be 4 and not bothered with the 3's at all. 4 pi r squared, if I'd wanted to do that. I'm going to go ahead and write that now, but I didn't want to skip that step and lose someone. So 4 pi r squared dr, that's what dv is. Okay, so the error in the output variable is this function of the input variable and the error in the input variable. So dv is a function of two inputs, r and dr. So I have an r number when the radius is 4, and I have a dr number when the error in the radius is 0.05. So I can plug those numbers in. So dv, and probably if I want to be super precise, put when r equals and when then dr equals, but let's not clutter our notation too much. We'll leave that out for now, at least for this first example. So if I plug in 4 for r and then 0.05 for dr, this gives me the absolute error in the volume calculation that I did up here. So basically, what is this? 16, well, I guess I can think of it this way. Let's combine these two first. So 4 times 0.05 is going to be 0.2, right? And 0.2 times 16 is 3.2. So I get 3.2 pi. Okay, which if you want, well, of course, this is also in cubic millimeters. It's an amount of error in the volume. Either we're over by that amount or we're under by that amount, right? We might want a decimal approximation. So I'll grab a calculator and do 3.2 pi. I get 10 let's keep 4 places, 10.0531. Well, 3 places is really enough, so 10.053, that's fine. Again, this is, of course, cubic millimeters. So about 10 cubic millimeters, which, it's not a whole lot, but you might say, well, 10, that's a big number. Yeah, but remember, it's millimeters, right? Cubic millimeters, and a cubic millimeter is pretty small, right? A cubic centimeter is, 1 milliliter. And this is a cubic millimeter, well, 10 of them. So it's like roughly 100 of that, 1% of a cubic centimeter. So it's really not that much. But relative to the volume, is it a lot? Is this a big error or a small error? What percentage of the volume is that? So really what we would want is the error in the volume divided by the volume. Well, the problem with that is we only have the calculated volume. We don't know the volume, right? So we can't say, okay, take the, like, okay, so we've calculated the volume based on a measurement that has some error, right? Potentially plus minus up to 0.05 millimeters. So we don't know the volume. If we did, we wouldn't be talking about this. So we don't have the volume, but we can say, well, as a proportion of our calculated volume, because it's an estimate, it's off by a little bit, but we'll say as much as we can. So we can say that dV over V, this is an estimate for my error in the volume. Well, dV we said was 3.2 pi. V was 256 pi over 3. Well, I can do a little bit of simplification. And of course, these are both in cubic millimeters. Get those pi's out of there. And I guess I could write that 3.2 is 32 over 10. In fact, maybe I should have started that way, but that's fine. So 32 over 10, which of course reduces, but we won't do that yet, over 256 over 3. So this will be, you divide by a fraction, you multiply by the reciprocal. This will be 32 over 10 times 3 over 256. I'm pretty sure these two reduce by proportion of 1 to 8. Yeah, 1 to 8. So this goes away, becomes a 1. This goes away, becomes an 8. So we get 3 parts out of 80. As a decimal, how much is that? 3 out of 80. So 0.0375. Now that's the relative error expressed as a decimal. I kind of want a percent for that. What percent error is that? So move the decimal place over 2 places. 3.75%. And is that a lot? Well, I would say that's a fair bit. It's not 20%, which would be a huge error. If you were trying to make ball bearings, or you needed a ball bearing to work for a certain application, like you got a bunch of them, you have to pick the right one that's going to fit what you're doing. And your measurement when you're picking is off by 20%, that ball bearing's not going to work. If it's off by 4%, well, maybe. Depends, I suppose. So, what error allowance is tolerable depends on the situation. As a reminder, this one here, this is the absolute error. Right? That's basically dV, the differential of the output variable. That's the error in the calculated value. When you divide that by the value that you calculated, this is the relative error. And again, it is an estimate of the relative error, because in order to really get the relative error, you want dV over V, the error that you had divided by the actual volume. But of course, we don't have that. So as a stand-in, we have to use the calculated one. Anyway, there's that example. The other thing I was going to refer to was another way of writing these things down, which you might see in a textbook or if you watch a different video. And I kind of alluded to this, where we had the radius is 4 that we've calculated, but we know the error is up to 0.05. So we can say, oh, well, the radius is anywhere from 3.95 to 4.05. So another way to write that, which especially in physics engineering, you'll see this. You might say, so let's say alternate notation. You might see R equals 4 plus minus 0.05 millimeters. So that means that's basically saying that dr is 0.05. And you don't know if it's plus or minus. The error is up to 0.05, but you don't know if it's over or under. So that's why there's a plus minus. So then we could say that the volume is approximately, I never got a decimal for that. So I'm going to need a decimal for this guy at this point. So 256 pi divided by 3. Yeah, 268 point, say 3 places, 268.083. 268.083 plus or minus that dV, the error, 10.053. And that's cubic millimeters. So one way to express the error is in these terms, and another way to express the error is in these terms, but they really mean the same thing. Same information is there. All right, that's the video.